Okay, welcome back, folks. Looks like we can get started with our today's work. And with what we have today, our standard announcement is that quiz 10 is due today, and the quiz number 11 is now posted, but we're pretty close to the end of the amount of weeks for the semester, so there probably won't be more than one more quiz after that quiz number 11. With where we're at so far, we're going to begin with new content, starting over fresh, turning over to the concept of integration. So here, we're really just going to be computing areas. Well, approximately finding the areas of various things, not like areas of circles, rectangles, triangles, and so on. What we're really trying to do is alluded to at the very end of the section 4.6 notes. So this is the topic that kickstarts integration. Looks like we'll only have a couple more lectures to discuss integration before we run out of time for the semester, but we'll do the best we can with the amount of time that we have. As far as exam 3 goes, congratulations on getting through it. I'll be grading this starting on Friday, but one thing I have to admit to you is that I, for some reason, thought it was a brilliant idea to assign 3 exams all in this 1 week. So it's going to be a pretty big grading set for me coming up on Friday. This one is probably going to be completed sometime either on Saturday or Sunday. As soon as it is, I'll post it over here, your grades, as well as the marked up copy of your exam with the information and solutions. So you can check out that same as you did with exams 1 and 2. But before we get started with our work today, any questions at all to start us out? Okay, well, let's jump back in. So we are in section 5.1, and here's how it starts out. It begins discussing the so-called area problem, our next interesting topic in calculus. We want to find the area of the region S in that diagram below. It's bounded by really 4 different things. The horizontal line, which is the x-axis described as y equals 0, the horizontal line at height 0. It's also bounded by 2 vertical lines, x equals a, x equals b. So these parts aren't so bad. If we had just straight line segments like we have here, 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 then we could find the area. But what's turning it into a bona fide area problem is the curvy part. We now have a curve, y equals f of x. We're going to, in this section, insist that that function is continuous. And this is what makes computing the area actually quite tricky altogether. So in section 5.1, f is going to be a non-negative function. So it's greater than or equal to 0 on the domain. But when we really get going on integration, we're actually going to allow it to become negative and extend on the topics that we see here. So this is the problem we want to compute, finding a way to approximate that area S. Any questions at all with the problem at the moment before we describe the solution? Okay, now imagine this was, for some reason, a really important problem. S could be a lot of interesting physical properties. It could be a distance, like we'll see in example 1. It could represent a physical force, like energy, kinetic energy of some kind. It could represent money, a population size. If you frame the problem just right, area could be just about anything, really. So if you had to approximate it, here's one thing you could do. We're not going to take this approach, but it's more for illustrative purposes. If you drew a rectangle like this, we could find the area of this rectangle, and then that area is a pretty big underestimate, right? Everything above has been cut off. So if instead we do a different rectangle going from here to here, we can find the area of that taller rectangle, but now it's a way overestimate. The white space is area we didn't want. And then maybe you could say average the 2 rectangles that we put down. It might be somewhat close to the true area, but that's going to depend on the curvature of this function y equals f of x. So there's lots of decent approaches to getting approximations. Here's the approach that we're going to be taking on these notes. We're going to take this interval from A to B and essentially just cut it up, write it out as a partition, and use not one rectangle, not two rectangles. We want to construct n rectangles. So n, we like to think of as being a large number, like say 10, 50, or 1,000. The ones we do by hand on paper are going to be more like 6 or 4 rectangles, so it doesn't feel like a whole bunch of busy work. But we'll construct n rectangles with equal width. That equal width will have a particular name that we're going to use in the formulas. The equal width will be delta x to match up with the x-axis. If that's a t-axis because it's time or something else, we might call it delta t and so on. So if they're all going to have the same width and there's going to be n of them, the way we get the formula for the equal width is we go from the b and the a, take that total length, b minus a. If there's going to be n rectangles, then we take b minus a divided by n. So we construct n rectangles of that equal width. This will be a common formula we use in these notes. And once we have those rectangles, we'll just compute the area of them. So let's describe that on paper on this example before we show how it goes on the example number 1. So let's imagine we did this. We have a delta x. My picture is not going to be for a generic n. It'll be for some value of n that fits in with this diagram. Once we have the equal width, the next process we'll take is find the endpoints. The endpoints, these are going to be the endpoints of the rectangles we're about to put on paper, will be x naught. So x sub 0 or x naught, that's just the starting point. In our problem, x naught is just a. So that's our x naught. Then if they're all going to have an equal width delta x, the way we get the next endpoint is we take x1 equals x naught plus delta x, whatever that number happens to be. So we're going to go a distance here, move over to the right by 1. Unit in terms of the length from here to here is delta x. Let's call this x1. So the width is delta x, and then because it has an equal width on every one of these rectangles, we just keep on adding a delta x to get all the other endpoints. So the next one is x2, is the prior endpoint x1 plus delta x. Here's the x1 in the diagram. x3 is x2 plus delta x. Oh, hang on, I forgot to call that a 2, or not forgot, just simply didn't. So there's x2, and next here's x3. And I'm trying to make them equal widths, so let me see if I can format this just a little bit better. Space it out just a little bit more. Here's 1, 2, 3. I think that's going to come out a little bit more equal. So here's x1, x2, x3, and if we add delta x again, for this diagram, we're going to end up on B. So here's x4, and we'll say x4, prior endpoint plus delta x one more time. So generically, there's going to be n rectangles, but in our diagram, we ended up on x4. So this is a diagram for n equals 4 specifically. And the reading, it shows some really nice diagrams for when computer graphics are given n is 10, 20, 50, 100, and so on, to show what happens when we draw those rectangles. We're doing it just once. Any questions at all, folks, with the equal width or setting up those endpoints? Naomi says, how do we know how many rectangles to use? Oh, the problems will always specify. Say for this one, it says, let's see here, use 6 approximated rectangles at right endpoints. So yeah, it's always going to tell us the number of rectangles that we're going to use in our approximation. So we'll always have that particular value. Thanks for asking about that. Other questions at the moment? Oh, and to answer your other element of your question, yes, we could have done an approximation with just 2 approximated rectangles. Absolutely. But the idea with our process so far is we'll see that the approximation to this area in blue will get better and better as the number of rectangles get higher and higher. So every value, even 1 rectangle, that's an approximation. 2 is better, 4 is a little bit better, and so on. There's diminishing returns, but the higher this value gets, the better and better our approximation becomes. And notice we're basically talking in terms of limits. Our approximation gets closer and closer to the true value of the area as the limit as n goes to infinity occurs. So that's how calculus becomes part of this problem. There's really a limit here for getting exact area versus approximating the area like we're doing here. With the diagram so far and all of our endpoints, we just have to draw the rectangles. There's lots of ways of doing this. The example 2 or example 1 down below is going to ask us to look into a right endpoint. We'll look into left endpoints and midpoints. And there's other interesting schemes for rectangles. For this scheme, here's how I'm going to do it. I'm going to use this interval here, draw some rectangle, but use the right endpoint, x1. What I mean by that is this x1 is going to determine the height of the rectangle by hitting the curve and calling that the height. So here's our very first approximated rectangle to the area S. And the height of that curve, that's just the function value, f at x1. So we have a height. We in fact have a width. I forgot to re-put that back. The width of this rectangle here to here is delta x. So if you have a width, delta x, and you have a height, f of x1, we can come up with that area. So let's start writing this down. Area is going to be approximately equal to, take delta x, multiply it by f at x1, and then we have 3 more rectangles because we're doing a picture for 4 approximating rectangles. So just repeat the process. Again, imagine these are perfectly equal widths. x2, the next endpoint, comes up, hits the curve at a height here, and that's going to be the new rectangle. Let me see if I can make that look a little bit better. Hits the curve here, here's the height, comes down, and that's the next rectangle. Almost has the same height, just a little bit higher on this one. Notice on our first rectangle where the red dot is now, that's going to be an underestimate of area because we're missing out on this part right here. But on the next approximating rectangle, this one is going to be an overestimate on the area because this part right here includes extra white space, which isn't included in the region S. So some of the rectangles are doing a good job in one way, some are doing a bad job in other ways. But nonetheless, it's just an approximation, so we can run with this to find the area of this next rectangle. Let me put a temporary arrow to point at it. The area for this next one is going to be the width delta x times f at x2. Notice that delta x appears twice. We could factor it out if we want. In fact, that's what we will do in the formulas. But for the moment, we're just building this step by step, so we're leaving the delta x on every single term. Then following the same logic, at x3, we draw a vertical line. Comes up, hits the curve at this height. This is another overestimate on the area of that rectangle due to that white space there. But when we find the area of this one, it's going to be plus. It's an equal width, still delta x. That's going to be the width times the length of the interval going from here to here. That's just f at x3. Then one last one. At x4, we go up, hit the curve right where it terminates, go to that height, plug in the expression for the area of that one, that's plus delta x, times f at x4. Or you could call it f at b if you prefer. So again, it's not a perfect way to get this area. There's a massive overestimate here, a massive overestimate. Excuse me, let me say that better. Let me start over. Here, that's a massive underestimate in the area because my area stops here and there's blue area above it. Sorry, I said that in the backwards direction. Here, this is an underestimate of the area. And these two middle ones are overestimates of the area. But what we can imagine is if n gets larger and larger, these underestimates and overestimates tend to get smaller and smaller. And so if we take a limit of this, this becomes the exact expression for the area. So far, it's just an approximation. We emphasize that here by putting the approximately equals to. And so area is equal to approximately. Here's how we'll typically write the formula. Delta x is a common factor, multiplying f at x1 plus f at x2 plus f at x3 plus f at x4. So that's our introduction to computing the area. Really, it has 3 basic steps. Step 1 is come up with the equal widths. Step 2, decide on which endpoints you're using, list them all. And step 3, just crank out that expression there. Well, any questions or comments at all, folks, with just the introduction of this topic? Naomi says, why do the rectangles go to different heights? The heights are determined by the graph at y equals f of x itself. So if we redo this one right here, actually, let's back off to just a couple. So we're not looking at the endpoint being b. So the question was, why are they at different heights? It's because the heights of the rectangles are determined by the endpoint specifically. So say if we're looking at x3, we're going to use f at x3 to be the height of that one, because if we want to give the best estimate possible, we're going to say the height of this curve should be where the area in blue, what we want to calculate, stops. And that area stops right here. So the heights are essentially determined by the curve itself. So that's why this one was a little bit taller. But when we went to our final point at B, the line goes here but stops because the curve stops right at that point. So we make it be exactly at that height. They're supposed to have equal widths, so the difference in the widths is just by the freehand drawing. Does that make sense for the question on the different heights? Yeah, absolutely. Other questions at the moment? Okay, well, let's try out one where we're going to go beyond just writing this down and actually put a number on paper. So I like this problem here because it gives us a good idea of what these area problems are really all about. So here's a first applied problem in this section. We're told the velocity graph of a car that's accelerating from rest to a speed of 120 kilometers per hour over a period of 30 seconds is shown. So it looks like it's just an average car. 120 kilometers per hour is not that fast necessarily. It's a long period, 30 seconds. So we have a time axis going this way, seconds. It's a velocity graph. So instead of calling this a y-axis, we have a v-axis for velocity. And this is our velocity curve that we're modeling. So the function is a velocity at time t. Now we're told, based off knowing the velocity, estimate the distance traveled by using 6 approximating rectangles at right endpoints. The last problem we were looking at, it was 4 approximate rectangles at right endpoints. We'll round to 4 decimal places, and also determine if we're giving a distance that's an overestimate or an underestimate. Okay, now one thing you might have spotted that is a little inconvenient about this problem is notice the units. I have seconds on the horizontal axis, hours on the vertical axis. So that is a unit mismatch that we have to navigate. So that's going to be our first thing to kind of want to correct on this one. But we'll go through it in the same exact steps that we indicated in the warm-up problem above. Step 1, we're going to draw approximating rectangles over this graph. We have to know the width of those rectangles. So we call this delta t. Not x this time, because this time it's a t-axis. We have a range we're finding this area over. It's bounded by the horizontal axis, starts at 0, ends at 30. So that means we're going from a time of 0 seconds to 30 seconds. So we're just finding the width of the domain of this function. So go 30 minus 0. We didn't have to do the minus 0, but in case the curve has a different domain, that's a process. Take the maximal value in the domain, the minimal value, subtract. It says 6 approximate rectangles. So we take that number, divide by 6. So that gives us a delta t, which is in units of 5 seconds. Kind of convenient to the graph. So we're going to go 5, 10, 15, 25, 20, then 25, and so on. So that's a convenient delta t. Inconvenient with a unit mismatch. So we're going to have to cross this bridge at some point. Let's also do a unit conversion. Delta t is 5 seconds. We need to get it to hours. So we're going to multiply by 60, or rather, let's say, let me try again on my units. 1 minute per the 60 seconds, multiplied by 1 hour per the 60 minutes. So once we throw that in, delta t, a couple ways you could give this. You could go 5 divided by 60 squared. If you go this route, you probably want to keep something like maybe 3 significant digits, which goes 0.00138, for example, or even a little bit farther, or else we'll round to bluntly on this one. It's kind of an inconvenient number, but another approach is take 60 times 60, 3600, then take 3600 divided by 5, and that tells us this fraction reduces to 1 over 720. I'll go that route because it's easier to write on paper. No approximating whatsoever. 1 over 720 hours is our unit. So we have it in seconds. Now we have it in hours. Next thing we should think about is, it's a weird graph, right? We have velocity, we have time, but we're told, come up with distance. So let's spend some time on explaining just how we're going to make that happen. Using formulas from college or from algebra classes back in the day, you can recall that distance is equal to rate times time, or we could say it differently. It's equal to times time times the rate. Like time coming first because time is going to be delta t. So I'm organizing the formula instead of rate times time. It's the same as time times rate. We have the time, it's in seconds, and we're going to be using these time intervals, 1 over 720 hours specifically. We have a rate. The rate is kilometers per hour, specifically that velocity. So we can find these distances, but the trouble is the actual rate of speed, it changes at every moment of time. But if we look into small moments of time, say 5-second intervals, we can just assume a value during that 5-second interval, and that's going to be the rate. Really, it's the same thing as what we did on the very last diagram. Next thing we're going to do, write down the endpoints. So the endpoints following the process from before, we'll call an x naught. Let me put it down below a little bit further. X naught is going to be the value on the far left where the curve starts. 0. X1, we can add 1 over 720 hours, but for our endpoints, let's keep them in terms of seconds. I think that'll be a little bit more natural to use. It'll be 5 seconds. X2, 10 seconds. X3, 15 seconds. X4, 20 seconds. X5 is 25 seconds. And X6 is 30 seconds. So those are all of our endpoints. Really, we're just going unit by unit here, ending on the 30 seconds, which is giving us where the curve terminates right at this point. So those are our endpoints altogether. And now, in view of what we did on the last graph, let's take a quick peek at that last graph. This was right endpoints. Right endpoints meant the height of the curve was at the rightmost endpoint on every one of these rectangles. So these are all right end points. And that's what the problem is asking us to do in this situation. We have really 7 points altogether, right? But if it says use the right endpoints, we're using these. So all those specifically are the right end points. So let's start calculating the distance, well, approximating it. The distance, here's our step 3. Distance is going to be approximately equal to, first let's add a little bit of notation. When it says 6 approximating rectangles using right endpoints, and the formulas at the end of these notes, we're going to call that R6. R because it's right endpoints, 6 because we're using 6 approximating rectangles. Then we throw in the formula. Distance is going to be approximately equal to delta t. Then we multiply it against, following the format exactly as we did before, velocity at the first right endpoint, 5 seconds, plus velocity at the next one, 10, and then just keep on adding. Velocity at 15, velocity at 20, plus velocity at 25, plus velocity at 30. So far, this is really just the formula with the endpoints just plugged in to our new function, the velocity function. On the next line, distance, we're going to plug in our values, take our delta t, 1 over 720 hours, and then multiply it against all of the velocities. At this point, let's start also sketching the graph. Velocity at time 5, that's going to be this velocity here. Let me add a little bit more numbers just to make this a little easier to visualize. That's 20 kilometers an hour, 60 kilometers an hour, 100 kilometers an hour, and this one, we're going to have to use the arrow strategy, is at height 120 kilometers an hour. So going by 20s, that means this one, we're visually estimating it. So anything in the right ballpark between 40 and 60, I think 50 kilometers per hour would do the job, would be the right value. So that's 50 kilometers per the hour. We're taking this whole entire rectangle to represent the distance the car traveled. It's a pretty big overestimate. We're saying that in this entire interval from 0 to 5 seconds, the car is doing 50 kilometers per hour. It's a bit of a lie, right? It starts at 0 kilometers an hour and just climbs up to 50 kilometers an hour. So it's pretty wildly inaccurate in that first rectangle. But notice that the area is a rate, that's the height of the curve, 50 kilometers per hour. It's also a time, that's the width, 5 seconds, or 1 over 720th hours, matching up the unit. So this area here, even though it's a poor approximation, it's giving us the approximate distance. Then we just do it again. We add on a new term, velocity at time 10 seconds, and keep on doing it until we have the remaining 5 down. But any questions at all, folks, getting just that very first term? Okay, well, let's do it again. Next approximate rectangle at time 10 seconds. Height here looks like it's just shy of 80 kilometers per hour, but we're visually estimating, so I'll call it exactly 80 kilometers per hour plus 80 kilometers per hour. And if you're ever asked to do this again on a real exam, again, as long as you're in the right ballpark, if you said anywhere between like 77, 82, you're not going to lose any credit. I'm going to look how close your numbers are. You might lose a point if you said that was 130 or 40, something like that, way out of the right range. So that's our next approximating rectangle. This one's an overestimate, but not as bad as the first one. Then rinse and repeat. Velocity 15 seconds in. We're saying that the velocity is approximately that value, just shy of 100, maybe about 95 or 97, depending on how you approximate this one. So we're saying for the entire range, 10 to 15 seconds, that's a time of 5 seconds. Again, 1 over 720th of an hour. We're saying that the rate of speed is, let's go with 97 kilometers per hour for that whole interval. 97 kilometers per hour. Then becomes pretty methodical after a point. At 20 seconds, we have this height. The rectangles keep on getting higher and higher, following the height of the velocity curve. This height looks like it could be maybe 110 kilometers per hour. So all that blue area is now represented as distance. This one's a tiny, tiny overestimate. Notice as the curve gets closer and closer to flat, as the tangent lines on each point gets closer and closer to 0, or as the derivative gets closer and closer to 0, these approximations get better. But the derivative is large here. The slopes of the tangent line are large. That's why this one's way, way off. But as it gets horizontal, our area estimates are just getting better and better. So on this one, at 25 seconds, let me try again. I think I can do a better vertical line than that. This one, the height here, it's about a height just shy of 120, maybe let's call it 115 kilometers per hour. And on the last one, we're told it actually reaches a speed of 120 kilometers per hour. So if we use this right endmost point, forgot to shade this one, let me just throw that on there. This last right end point is exactly at 120 kilometers per hour. So now this distributes into the group. We're going to follow order operations instead of distributing. But when it does, we've just calculated distance equals time times rate 6 different times to correspond to these 6 different intervals that we computed. So every one of these areas represents a distance. All we have to now do is throw it into the calculator and get a value out for approximate distance. Okay, let's throw that in. At this stage, if you put it in at that format and you're using the decimal number, again, try to keep at least 3 or 4 significant digits. You'd be just fine along that approach. I'll use the fraction just so that there's already an approximation here. We'll keep it more accurate by not approximating that one again too bluntly. So as its exact value, 1 over 720, we'll multiply 50 plus 80 plus 97 plus 110 plus 115 plus 120. And this is the figure we get. To 4 decimal places, it's 0.7944. Kilometers. So by this estimate, with 6 approximate rectangles, we're saying the car traveled that far. How could we improve this? Take 60 approximate rectangles and imagine what this graph would look like. It would be a really interesting sawtooth pattern where it's like a jagged step ladder going up along this curve at 60 approximate rectangles. There's still going to be overestimates, but they're going to be tiny now at 60. And as this gets larger and larger, our area estimate gets closer and closer, which means the estimate of the true distance becomes better and better, more precise at higher number of subintervals. So we have found the approximate distance to 4 decimal places. As far as whether it's an overestimate or an underestimate, our rectangles include these area segments that are beyond the curve in red. All of these are overestimates, every single one of them. So we can say here, this is an overestimate. So that's a process of getting an area. If we could find out what the function is, model this curve with a real mathematical function, we could use calculus together with antiderivatives to do this exactly, no approximate rectangles whatsoever. But this is the concept before jumping into the fundamental theorem of calculus, where limits start to take over. Any questions at all, folks, on the full conclusion with this one? Okay, pretty much this is what's going on with the quiz. The quiz is a little bit different. It doesn't give a graph. We're going to produce our own graph to go along with it, but it's the same kind of idea of what we did here. So this one was using right endpoints, and the math would be totally different if we used left endpoints. Or maybe we could decide that the height of these curves should be at a height midway between 0 and 5. We'd call that a midpoint instead. So again, there's a lot of interesting ways to determine which kind of points are you using in the first place. And so that's what the next couple examples are going to be all about. So example 2, we're going to do 2 parts. First one, it says, use 4 approximate rectangles at left endpoints. And we're going to find the area under the graph. F of x is the natural log of x from 1 to 9. Round to 4 decimal places. And first thing we have to do on this one is sketch the graph of the curve itself. Then we can throw the rectangles on it. So if this one was a true exam question, the graph would be provided like we're about to provide ourselves. So let's make that our first step. Just visualize the function, and then we'll be able to draw the rectangles under it. So let's get a good graph going. Let's say f of x, natural log of x. That's a domain that we're considering. We're only working from 1 to 9. So let's also say further, 1 is less than or equal to x, which is less than or equal to 9. There's a better looking graph of our function. Let me kind of zoom out. I can make this show up a little better. So there it is. There's our entire function, natural log x from 1 to 9. So this is what the problem would look like if it was a true exam question, say now on the final exam. The graph is provided just like on the last problem. And so we don't have to worry about hand sketching any curves. I think that's going to go beyond the concept that we'd want to test on for a real exam. So now that we have the graph of the natural log x, let's actually give it its name. Next thing we want to do in this process is, in step one, we want to eventually sketch the rectangles now that the graph is there. So in order to do that, we need to know the width of those rectangles. So this is the next component, delta x. Delta x takes a b value, which is 9 in this graph, minus the a value, which is 1. So the formula always goes b minus a divide by, we divide by a number n. So for the information given, a is 1, b is 9, n is 4. So plug that all in, and delta x becomes 9 minus 1 divided by 4, which is definitely convenient in a certain sense. So if you look at this closely, this is now just a to divide by 4. So that means the width of all these rectangles are 2, which is pretty compatible with the information on this graph. It's not too bad to plug in those values. So after we have the equal widths, next step, we want to list out all of the endpoints. Paying key attention to this time, we're dealing with left endpoints in the problem. So here's our step 2, the endpoints themselves. The leftmost endpoint, x naught, is always where the curve starts, the value a given, which is 1 in this problem. So we're starting right at 1. Then to get all of the other values, just like we did on the last graph, all you ever do is add delta x repeatedly. So if our first value is 1, the next value is 3, adding 2 for delta x. Then likewise, x2 is going to be 5, x3 is going to be 7, and there's a built-in check here because we have to end on 9, and if n is 4, we're going to have 5 endpoints. So next one, x4, add delta x, which is 2 to the 7, we get 9. So we landed on the 9 that we have to end up on, and there's 5 endpoints altogether. So there they are. Let's put them on the graph as well. So here's 1, 3, 5, 7, and 9. So our hand-drawn points are points that we're going to use. But now we're going to look into what is specifically left endpoints versus right endpoints. First, any questions or comments at the moment with the work we've got? Okay, to me, this is sometimes the trickiest bit about the whole process. If it says left endpoints, first let's review on what we did for right endpoints. When it says right endpoints, that means we were going specifically through these values. We end up on the rightmost point on the boundary of the domain, 30 seconds. If you say left endpoints, this whole rectangle kind of just goes like that. That's what left endpoints look like. You use the leftmost endpoint instead of skipping it, like when you use right endpoints. So on right endpoints, you skip the left endmost endpoint. But now on left endpoints, we're using these. All these here are the left. Hang on, I grabbed it wrong. Let me try again. All of these here, using the leftmost endpoint. There we go. 2 tries is the charm on this one. These are the left endpoints. So left endpoint means you use the leftmost endpoint is a great way to think about it. If it's right endpoints, you use the endpoint to the furthest right, skipping the one on the furthest left. So that's the only difference between saying left endpoints and right endpoints. But I think it definitely gets kind of tricky once we throw in the left endpoint rule. Any questions at all, folks, determining the left endpoints? Okay, once we have that on paper, step 3 is just going to come up with the area. So like we did before, let's write down the formula. Then we'll input the values, sketch the graph as we go. So the area is going to be approximately equal to, on the last problem we called it R6 because we were using right endpoints with 6 approximating rectangles. But this one is asking for left endpoints. So we're going to call the area approximately equal to L4. So that's just a name that comes up here and there in the notes. If it's left endpoints, that's just the shorthand way of saying that, L4 for that. By formula, the area is going to be approximately equal to, now plugging in these values, we're taking delta x multiplied by, here's the graph, f of x equals natural log x. Down below is the graph rather. This is the function definition above. It's going to be f at, first, this endpoint 1, plus f at 2, excuse me, not 2, didn't look at my point too clearly, at the next one, which is 3, plus f at the very next one, 5, plus f at the last one, 7. So it definitely looks a lot different from the last problem. We don't add f of 9 to this one because that's going beyond our left endpoints. But one thing that kind of matches up with all the problems we've done so far is if it's 4 approximating rectangles, there has to be 4 terms inside this group right here. This just happened to use the leftmost endpoint and not the furthest right endpoint this time for the left endpoint rule. Now from here, we're going to just plug in values and sketch the graph as we go. So next step, area approximately equal to, we're just making substitutions, throw in 2 for delta x. On the graph, first one is f at 1. F is the natural logarithm, so we're going to rewrite this as natural log 1. But when you think about natural log 1, sorry, that was too big, let me fix that. Natural log 1, or the logarithm to any base at 1, is just 0. That's the height of the graph. It should be at height exactly 0, meaning we're getting no area. And that's because if we're using the left endpoint rule, the height of the graph depends on the left endpoint. It depends on the height of the function at 1, but the function height at 1 is 0. So this is our first approximating rectangle. It's kind of just degenerated into a line segment with area 0. So we're going to get a 0 on the very first term, which is definitely weird. But that's what the calculator is saying is we're going to get as well if we follow this process. So following the math doesn't look too concerning, but on the graph, definitely weird, right? That is a humongous underestimate of area. We've lost all of the area in this region here. But then when we go on to the next term, it's not as bad on every single term. We do plus f of 3, which means natural log 3. And that just means natural log 3 is the height of the next rectangle. So draw a line that stops here. The height of that is natural log 3. It's a rectangle that goes from 3 to 5 because the width has to be 2. I should try again on that. Let me try one more time. So there's our second rectangle, but this time our first real rectangle with an actual positive area. And that's because natural log 3 is positive. Then keep on going in this particular process. Plus, f of 5 just means natural log 5. This endpoint at 5 determines the height. At 5, we go up, stop at this height, which is now at natural log 5. That height determines the height of the rectangle from 5 to 7. And then one last one. F at 7 is natural log 7. On left endpoints, you start at the 7, go up till you hit the curve, Here's natural log 7, and that's going to represent the height of the function in this entire region from 7 to 9. So that's the area for that entire segment. And we're pretty much there. We just have to throw this whole result now into a calculator. This one is asking us to round to 4 decimal places again. But before we just drop it into the calculator, any questions with the formula side or comparing it against the geometric side, the graphs above? Haley says, so with the graphs that go upward as x gets bigger, if you use left endpoint, it will always be an underestimate. And if you use the right endpoint, it will always be an overestimate. Yeah, that's exactly right. Let's put that on paper just as he said it. There's lots of different ways to say it. And we can say loop in the fact with, well, I guess they were both increasing. If we had decreasing graphs, it'd be the same ideas, but just backwards. Let's say it's here for the increasing graphs. If the graph is increasing, then it's an absolute fact, just as Haley observed, R, so right endpoints at n, however many subintervals you use, 6 or 4 and so on, is an overestimate. And ln is an underestimate. So this is a true mathematical fact each and every time. That now that you mentioned that, if we extended even beyond these topics, this is something that gets done in other calculus courses. We've spent more time approximating these rectangles. You would find that, well, if Rn is an overestimate and Ln is an underestimate, why not just average them both, right? The true area has got to be somewhere in the middle. And that's in fact another process for finding the approximating rectangles. This is the so-called trapezoid rule. Does the following. It takes the right endpoint plus the left endpoint, averages it divided by 2, and it's an even better approximation. Oh, other questions or comments so far? Okay, well, let's put our approximation down on paper now. We've got the area of this curve. No physical fact behind it because it was missing context. We're just focusing purely on area. It is 2 times. You could skip natural log 1, but let's just throw it in to observe. Yeah, that's definitely 0, plus natural log 3, plus natural log 5, plus natural log 7. And here's what it comes out as. To 4 decimal places, 9.3079. Let me double check that just to make sure. Okay, yeah, it looks like we've got it. So that's area so far in a nutshell. Like we mentioned quite a bit, if the number of approximating rectangles gets just larger and larger and larger, this approximation becomes more and more precise, more close to the true actual area of this curve. What that means is, if you want to define the actual area under this curve, here's what it looks like. It's a bit of a mess, but hey, we have the exact area. You take the limit of either the right endpoint rule with n approximating rectangles. This is what it would look like. And if we use sigma notation, we'll explore that in the notes as well. This is just a compact way of saying the same information. But notice there's no approximation here. The area is defined to be the limit of the approximating rectangles at right endpoints. But if you use left endpoints, same exact area. As the number of approximating rectangles goes to infinity, these approximations get better and better, and in the limit, it results in the true actual area itself. Here, the delta x is left on the inside, just distributed in. We factored out our delta x to make by hand computation a little bit more workable, so it doesn't feel as much like busy work. but these are the major ideas. And it says it doesn't actually matter if you're using right endpoints or left endpoints. If you take random sample points that are just somewhere in each one of these rectangles, that's what the x1 star, x2 star are, the limit still comes out as the exact area. So we're going to explore this a little bit more. We have basically two more problems to take a look into before we close out the notes. So the next problem we want to explore is if Rn gives an overestimate, Ln gives an underestimate, you could do both and average them, the trapezoid rule. Our book doesn't go into that one, but it's an interesting and kind of a cool fact. But another idea is, what if we let the heights of every one of these rectangles be at the midpoint, midway between 1 and 3? Let's just put down a temporary rectangle. I'll take it off so the notes don't get too visually oppressive. But if we use a midpoint at height 2, and this is our rectangle, notice it has kind of a compromise. To the left, it is overestimating. That's too much area. On the right, it's underestimating. There's area right here now where that wedge is. But there's a pretty decent balance. Not perfect, but there's a decent balance between the overestimate and the underestimate if we use midpoints instead of left endpoints and right endpoints. So that's the next one we're going to practice in the very next graph. So looking at the time, this one might be our last problem for the day. I think this one is a little bit trickier, so we're going to absolutely take our time with this one. We have a graph. F of x is 1 over 1 plus x squared. We'll produce our graph as well using Desmos. But again, just as a reminder on a real exam, I'll have that graph printed so that you don't have to worry about hand sketching any of these. We'll focus mainly on the calculus aspect. We want the area under this graph from -2 to +1. So already that's a new element. One of the boundary values is negative, which is absolutely allowed. We're using 4 rectangles now at midpoints. So not the left endpoint, not the right endpoint, halfway between those. First thing we'll do is let's throw the graph onto the document. In hindsight, I probably should have just done that when I typed out these notes, threw the graph on it. But let's put it on the paper here. F of x is 1 over 1 plus x squared. But like the others, it has a domain issue. X is going between -2 and +1. So there's our graph, that tiny little region there. Let me try to take a decent screenshot of this. And that should do the job. Okay, now let's leave it big like that, just so that we can really focus on what's going on if we're doing midpoints this time. So midpoints are kind of tricky. We want to put down still all of the endpoints because the endpoints are where the rectangles start and where the rectangles end. But once we put in all the the endpoints, you have to get the midpoint, which is going to be the height of the rectangles. So there's kind of an extra step in the middle of this one. Let's write out our steps more carefully this time. Step 1 for this process, find delta x, just as before. So our values come from this information here. This is telling us A is always the smallest value to the left, -2. B, the largest value to the right of +1. N is the number of approximating rectangles, 4 in this problem. So that gets us started. Now we can write out that delta x is, we'll take -2 minus, hang on, got that backwards. You know, probably would help me if I wrote down the formula. I was subtracting backwards and wondering why I'm going to get a negative value. Delta x has to always be positive. So that's an important fact to keep in mind to not get mixed up in the middle. So my delta x is going to be the b value, which is 1. So there's where my sign error is, minus the a value, which is -2, divide by n, which is 4. So delta x is the numerator 3 divided by 4. The fraction's kind of inconvenient. I think it's a little bit easier in this problem to put in the decimal number, which would be 0.75. So that's our delta x on this one. So the last problems we've been taking a look at were kind of rigged so that everything just falls perfectly on the grid that we see. But occasionally the delta x value, the number of rectangles, don't line up exactly perfectly. So that's another thing that's going on in this problem. So now that we have the delta x, step 2 is find all endpoints. This part isn't too bad. If n is 4, there's 5 endpoints. We are going to find the midway point on every one of them, which is going to be 4 midpoints. First one, x naught, is the far left endmost point, so -2. Next one, x1, we're doing the same as what we've done before. We're adding delta x to get all the other endpoints. Delta x is 0.75, so we're going to get -1.25. On the next one, x2, keep on adding that, is going to be -0.5. x3, take -0.5, add 0.75, and it's 0.25. x4, add 0.75 to x3, and we get exactly 1. Then we check. 1 does in fact match with our boundary point here. So these are all the endpoints. And because we're going to graph the rectangles, we need to put these endpoints on the graph as well. So let's plug in, well, -2 is already here. I'll just label it as x naught. x1 is a -1.25, which is going to be about, let's see. So that's in units of 0.2, so 0.25 is about here. So here is x1. x2 is at -0.5. x3 is at 0.25. And x4, hang on, I think I'm putting these values down a little bit weird. Let me double check my work here. x1 is -1.25. So that looks about right. x2 is -0.5, so about here. x3 is 0.25, so that should be about here rather. Here's x3, and this one, -1.25. x1, I think that's what was throwing me off there, should be about there. Finally, over here is x4. So the rectangles are going to go from these bounds to every one of those endpoints, but the heights of the rectangles are going to be the values midway between each of these values we put down. So that's going to be our step 3. Find all midpoints. And the name we give the midpoints are x bar. X bar typically means average in the statistics context. And it's a good symbol because the midpoint is going to just be the average between these two values right here. So x bar 1 is going to be -2 minus 1.25 divide by 2. So average those values. Let me minimize this calculator. So -2 minus 1.25 divide by 2 gives us a -1.625. So that's our very first midpoint. This probably needs its own color coding altogether. So let me use blue for all of these. Here's X bar 1, roughly about here. So lots going on in this diagram, but once we have the first midpoint, let me see if I can get that to look a little bit better by eye. About here. That's going to be the height of the first rectangle. So the first rectangle goes to this height directly above X bar 1, moves over to the left. Imagine that's a perfectly horizontal line. Moves over to the right. It goes on the extent of the endpoints from X0 to X1. So this is our first approximated rectangle. Definitely a process on this one. So the midpoints, if this comes back as a final exam question, the rest of the exam has to be shorter just because of this one question. I'm never going to ask you to do this with like 8, not even 6, probably 4 is as high as I would go if it's a midpoint problem. There's plenty of steps to show just for this one. Now we do it again. We need the next height of the curve, which is at X bar 2. But here's where a nice little mathematical miracle occurs. X bar 2 is the average between negative 1.25 and negative 0.5. But here's the other fact. The distance from all of the midpoints is delta x away from each other. So a great way to calculate X bar 2 is to just take X bar 1, add delta x to it, and that's a much nicer computation. So if we go this route, X bar 1 is negative 1.625, add delta x, 0.75, and we get to negative 0.875. And just to double check, if you did the average process, here's what it would look like. The second midpoint, X bar 2, is the average of X1, X2, so it would be negative 1.25 minus 0.5, divide by 2, and you get the same value either way. So adding delta x is just a little bit faster. So that's our second midpoint. Let's add it to the graph. Negative 0.875, somewhere around here. It's got to be between X1 and X2. So I'll just drop it here by eye. Here's X bar 2. Once you have X bar 2, it determines the height of the next rectangle. Go vertically above, throw a point on the curve for the function in green. And we go up through here. Dang it, let me try again on that. Go up through here. And again, notice the rectangle goes between the actual endpoints, X1, X2. And here's our next approximating rectangle. Like before, it's a compromise. That highlighted yellow region is an overestimate of the area because we want the area under the green curve. But in this region, our rectangle is an underestimate because the green curve is higher than it. But these two areas, they kind of balance. They're not exactly equal by any means. But when we add the overestimate, subtract the underestimate, when we balance them out, they come out close to a net balance of about 0. So the bias is smaller using these midpoints. Well, let's keep on going. Take X bar 3. It's X bar 2, add delta x again. But in your calculator, you don't have to retype these. All you really have to do is, if you're adding delta x again, just go plus 0.75 again. Or if you're adding delta x again, that means you're just taking this and going times 2, however you'd like to do it. I think in a normal calculator, you'd usually be punching in plus 0.75. So let's do it that way to make it feel similar to a calculator. That would give you a negative 0.125. So that's the penultimate midpoint. We're almost there. X bar 3, pretty close to 0, right around this range between X2 and X3. Negative 0.125 is about here. Then rinse and repeat. Once you have that point, go vertically up from it on the graph. Here's the next height. The rectangle now comes up through that point, but stops where x3 is. Vertical lines have been tough today. Let me try again. There we go, and that's our next rectangle. Notice another interesting feature about this geometry. If the curve has a turning point, if it went from increasing to decreasing, the midpoint rule fails on the turning point. It's an overestimate on both regions. So if you had a curve like a sine wave that did this, and you did a midpoint rule where the midpoints were at the peaks of every one of these curves, now the midpoint rule is actually doing pretty badly. The trapezoid rule, averaging the left endpoint rule and the right endpoint rule, probably is going to do a little bit better. There's really a lot that goes into this context of approximating areas. The geometry of the curve itself can make things go right, or it can make things go wrong in odd ways. Here's where it went wrong a little bit. Even though the midpoint rule is fancy, that wasn't the best approximating rectangle by any means. An overestimate purely. Well, let's put one more down on paper, x bar 4. It's the prior midpoint, x bar 3, add the width of all these rectangles, delta x at 0.75. In the calculator, just add 0.75 literally. We get our final midpoint of 0.625. And 0.625, midway between x3 and x4, I'll put it about here. Here is the fourth midpoint. We go up, just as before, hit the curve at that height. Now that it's at that height, that means we have to go horizontally to the left from there, stopping at x3, horizontally to the right from there, stopping at x4, which is 1, the boundary of the function's domain. And we've got our last approximated rectangle. That means we're ready for step 4, but I'm watching the clock as we go. Again, it's kind of a long process, unfortunately, with the midpoint rule. It's an important rule to consider, but for step 4, we'll have to come back to on this one. I definitely don't want to rush through this in about 2.5 minutes. So when we come back Tuesday of next week, we'll finalize this midpoint rule, actually fully approximate the area. We'll discuss a little bit more about summation notation like we see here and how it loops in with the definition of area, bringing in the limit. And then we'll show how to use calculus in the next section that we cover on finding these areas exactly so that we don't have to always draw a painful graph like this. But we did it, folks. Discussing the area problem is a little bit tedious at first, but it's just one section. Then we're going to actually use all the machinery that we've been developing, derivatives, antiderivatives, then the fundamental theorem of calculus to show how you get the antiderivative of something like this in essentially just one step. Well, it'll feel like one step at least by the work we've done on this problem. But any last questions at all, folks, with where we've ended on so far on this part B? Okay, well, have a great weekend, folks. I appreciate everyone's hard work. We've gone through the third exam. So on week 14, it's going to be just more work. Wherever we end on, it's going to be the extent of the entire course. And for week 15, we're just going to be fully reviewing for the final exam. So in a certain sense, we're pretty much there. But have a great night, folks. I'll see you all on next Tuesday. Yeah, kind of strange.